Okay, so this is the first video dealing with balancing of overall redox equations. We've already looked at balancing half reactions, but now we're looking at the whole thing. So first type of balancing we're going to look at is balancing by assigning oxidation numbers. So this is sometimes referred to as the electron transfer method. So before we get started on that, just quickly balance this equation, magnesium hydroxide and hydrochloric acid. So this simple neutralization reaction. If we were to balance this, we'd look at the Cl2 here, and we'd probably make that 2HCl to balance the chlorines. We'd look at magnesium next, its balance, so we have to now balance the oxygen and hydrogen. 2 times H plus 2 times H is 4. If I make that 2 waters and check my oxygen, 2 and 2, I see it's balanced. That's balancing by inspection. And so you've done that in previous incarnations of chemistry in earlier grades, and that's pretty straightforward. You just kind of look back and forth, and there's certain strategies you've followed to do that. Well, let's have a look at this one and see how we go with this. Okay, so try to balance that one by inspection. If you're to get started here, you'd probably look at all the sulfates. So maybe you'd attempt the sulfates first, which you can do. Well, why don't we try that? So we have 3 over here, 4. We have 4 sulfates. We have, so which one are you going to make 2, or which one are you going to make 3? Well, I notice I have 2 iron, so why don't we make that 2 iron 2 sulfate? Now I have 4 or 2 and 3, and that's still 4. So what if I make that 2? Now I have 2 sulfates. 2 times potassium to balance the potassiums. The permanganate's balanced now. And I can look at balancing using water. And so if I count the hydrogens, I have 4, and here I have 2. So if I make that 2, now I count the oxygen. So I have 8, 16, 24 oxygens. And here I have 4, 8, 20, 22 oxygens. So it's not balanced. So I have to start again. So I would do this, I'd erase everything, and I'd have another go. And hopefully you can see that's not a very good way to go about things. This is actually a redox equation. There's a simpler way. So let's look at that simpler way. All right, so just a quick read here. So I'll just quickly explain it. You might want to pause it to read it in a minute. But so again, the useful feature of oxidation numbers is they provide an easy means of tracking, and I've mentioned this before, tracking electron transfer. So we can, by assigning oxidation states, see the number of electrons that move from one species to another. So then what we can do is balance the electron transfer in species that have been oxidized or reduced. Rather than dealing with the whole complicated equation like that last example, we just look at what's been oxidized and reduced. And so in so doing, we pretty quickly balance the electron transfer, and that greatly simplifies any other balance by inspection we have to do. But ultimately, it still is balance by inspection. So here's a simple plan that allows you to kind of get through this. First step, assign oxidation numbers to all elements. You should be pretty good at that. You're going to see what's been oxidized or reduced, and you're going to identify the oxidation and the reduction, and I'll show you how that's done. You also are going to determine the number of electrons lost or gained. So in an oxidation, you identify how many electrons have been lost. You're going to balance by mass that atom that has been oxidized or reduced. And so specifically, if you identify an oxidation, and if those 2 atoms of that oxidation are not balanced, you balance it by mass. If you balance by mass, if you have to change the coefficient, you then change the number of electrons that has been transferred. And I'll show you how that works in a minute. But that's very important. If you change the balance by mass, you change the number of electrons transferred. You then make the total number of electrons transferred equal between the oxidation and the reduction. So now what we're looking at is we see an oxidation with a certain number of electrons transferred. That has to be matched by the same number of electrons being gained in the reduction. And so to do that, you simply find a whole number that balances those 2 electron transfers. Now these change these coefficients you're going to insert could be temporary. You might have to change them later. I have an example of that in a minute. You finally balance the remaining terms by inspection. So we've done that, but it's usually far simpler because you've eliminated a lot of the complicated balancing by balancing the electron transfer. And as a final check, it never hurts to rewrite the balanced equation and check that it's still balanced. Okay? So about a 5-step plan to get you through balancing some of these complicated equations using the assignment of oxidation numbers. So let's look at some examples. Alright, first one, balance this equation and use the electron transfer method. So step 1, assign oxidation states to all atoms. So here we go, -2 for oxygen, +1 for potassium. That leaves the manganese ion or atom as +7. Now you're going to see pretty quickly manganese is often oxidized or reduced. Oxygen -2, hydrogen +1, chlorine leaves the chlorine atom as +3. Likewise, chlorine in an equation is often the one that changes. -2 and +1 for oxygen and hydrogen and water. So here we go, -2 for oxygen, leaving manganese is +4. So there's a change in oxidation state for the manganese. So we'll get back to that. -2 for the oxygen, +1 for the hydrogen, leaving chlorine as +7. So there's our other change in oxidation state. And so there are the rest of them. So no change in potassium, no change in oxygen, no change in hydrogen, but we do have a change in manganese, +7 to +4. So this is what I mean by identify the Leo and the Ger. So +7 to +4, the oxidation, there's been a decrease in the oxidation state. That is a reduction. So that's a Ger. And how many electrons have moved? Well, a change from +7 to +4 implies 3 electrons have moved. Okay? So there's my Ger. Now I'm going to identify the other change. So chlorine +3 to +7. So that is oxidation state is increased. That is our definition of an oxidation. So that's a Leo. And it's increased by 4. And so that implies 4 electrons have been transferred. So that's what I mean by identify the number of electrons being transferred. Just write it down there to keep it front and center, how many electrons are moving. Next step, and a step that's often forgotten, balance what's been oxidized, that would be chlorine, or balance what's been reduced, manganese, by mass. Just these two terms. So manganese, there's 1, manganese, there's 1. So it is balanced by mass, so we don't need to change it. Chlorine to chlorine, it is balanced by mass, so we leave it. Okay? But don't forget, you'll see another example, you have to do that. If you forget it, it becomes quite complicated. Next step. Make the electron transfers equal. So what I have here is a reduction that requires 3 electrons. I have an oxidation that provides 4. Well, that's not equal, and they have to be equal. So I'm going to make these two numbers the same. That is, make the electron transfer equal. And to do that, I look for factors. And so a factor here would be multiplied by 3. So that's going to make it 12 electrons. And I'm going to multiply this by 4, and that's going to make it 12 electrons. So 3 electrons times 4, 12 electrons gained, 12 electrons donated. So that balances electron transfer. So what I now do with these coefficients, these, is when I do that multiplication, I bring it up here. So 3, 3, 3, 3. There we go. I've multiplied those two terms by 3. So basically what I'm saying now is 3 chlorines lose 3 electrons each. Sorry. Lose 4 electrons each, providing 12. And so the same here. I've multiplied by 4, so this becomes a 4 permanganate, and that becomes 4 manganese dioxide. So I've balanced the electron transfer. So right away you see how many terms I've balanced by that simple, fairly simple process. Now all I have left is hydrogen, oxygen, and potassium, those species that did not exhibit any change in oxidation state. So I'd look here first. I have 4 times K, so I'm going to make that 4 times potassium. Now I just have oxygen and hydrogen, so you might as well pick one and balance it and see what happens. So let's pick oxygen. So I have 4 times oxygen, that's 16, plus 6, plus 2. That goes to 8, plus 12, plus 4. So that's 24. Times O, and currently I have 22 times O. So how do I make those two equal? Well, notice this is the only term left that I haven't balanced. I can make that 2 water, and if I make that 2 water, I add 2 more, and so that becomes 24. And so now it's balanced. And as I said, I'm not going to rewrite this, but it doesn't hurt to quickly recheck it. And so I'll do that here. Let's just check all our terms. So potassium, 4 times K. Over here, 4 times K. Manganese, 4. And what do I have for 4 Mn? What else do we have? We have hydrogen, so I have 3 times H plus 6 times H, so that's 9 times H. And what do I have on this side? I have And so what do I have next? Hydrogen. So I have 3 times hydrogen plus 4 times hydrogen. That's 7 times hydrogen. And over here I have 3 plus 4 is 7 hydrogen. What's next? Chlorine. 3 times chlorine. And over here 3 times chlorine. And finally, oxygen, which we did last, and we know the oxygen's balanced. So that equation as written is balanced. So there's the procedure. Assign oxidation states. Identify the number of electrons being transferred. That's what's circled in red. Make the oxidation and the reduction the same by finding this common multiple. So times 3 and times 4 make the electron transfer 12 lost equals 12 gained. Make sure to make those coefficients in front of the oxidation and reduction. Finally, balance the rest by inspection. So it's pretty straightforward. It does take practice, so let's try another. Okay, so this one a little bit different, but we'll deal with it the same initially. So here we have dichromate plus hydrogen sulfide yielding chromium-3 and sulfur, atomic or elemental sulfur. So assign oxidation states, -2 for oxygen, +6 for chromium. You should realize by now chromium is often +6, +1 for hydrogen. That makes sulfur -2. Chromium-3 is 3, and sulfur, elemental sulfur, is 0. So again, identify the oxidation and the reduction. Well, there's our chromium, +6 to +3. That's a GER, 3 electrons gained. Now, sulfur, -2 to 0. That is a loss of electrons, and 2 electrons have been lost there. Okay. Now, the next step, which is often forgotten, balance by mass. What's been oxidized, what's been reduced? Well, notice sulfur and sulfur, it's balanced, but chromium is not. Cr2, Cr. So we have to balance this term by mass, and to do that, we make it 2 Cr3+. 2 Cr3+, 2 Cr, balanced by mass. And then we change the electron transfer. This is what's important. Each chromium gains 3 electrons. Therefore, if I have 2 chromium atoms, I've gained a total of 6 electrons. Again, total electron transfer. That's what that is implying. So 2 atoms require 6 electrons in total. So balance by mass, change the amount of electron transfer. Now I look at balancing the oxidation and reduction. This is 6, this is 3. So again, I'm going to multiply this by 3. And when I multiply this by 3, I just write a 3 in front of those 2 terms. So 3 times S, 3S. It's still balanced by mass. And I haven't changed the electron transfer because I've made it the same. So now I have everything balanced. But if you were to check this now, you'd realize it's not balanced because I don't have any oxygen terms here. So we've already done this. This is in solution. So we can balance oxygen by adding water. So we're going to add 7H2O. So there's 7H2O, 7 oxygen, 7 oxygen. I've now changed the hydrogens. So there's 14 hydrogen here. I have 6 here, so I need to add, like we did before, 8H+. So now I've balanced the hydrogen. And so this equation now should be balanced. And so let's check it. 2 times chromium, 2 Cr, 2 chromiums. Hydrogen, 8 times H, 8H plus 6H is 14, 14H on the right. Oxygen, 7 oxygens, 7 times oxygen, sulfur, 3 times sulfur, 3 sulfur. Balanced by mass. But we have quite a few charges here. Let's make sure the charge is balanced. If charge is balanced, we're good. 8 plus 2 minus equals 6 plus. On the right, going to 2 times 3 plus 6 plus. So it's balanced as written, and we can now comment on the solution. That's acidic because of the presence of hydrogen on H+. So that, don't let the fact that you suddenly have oxygen by itself without anything else throw you, because you can just add water, means you're going to add H+, and you'd stop there, unless the question says that it's basic, and we'll get to that later. All right, one last example. All right, so again, assign oxidation states. Hydrogen iodide, +1 for hydrogen, making the iodine -1. -2 for oxygen, making the lead +4. And that's going to be a change, I'm sure. -1 for iodine, +2 in this case for lead. So there's their change in oxidation. I2, elemental iodine, 0. So there is a change. +1 and -2. So no changes for hydrogen and oxygen. And you see that's very common. Hydrogen and oxygen don't change unless you have elemental hydrogen and oxygen. So let's look at changes in oxidation state. Well, we do actually have a change for iodine, -1 to 0. And so that is, the oxidation state is getting higher. That is a loss of electrons or an oxidation, and 1 electron has been transferred. Lead, let's look at lead. So lead going from +4 to +2, and that is a gain of electrons. And we have gained 2. So there's our oxidation and our reduction. Now, balanced by mass, what's been oxidized and reduced? So lead to lead, it's balanced. Iodine, 1 iodine to I2, it's not balanced. So I just add a coefficient here, 2. I'm not worried about this I2 at the moment, just what's been oxidized. In this case, the iodine of hydrogen iodide has been oxidized to I2. That's the only thing I'm worrying about balancing. Okay, so I've balanced by, and so by the way, I then have to change this to 2 electrons because I changed the coefficient. So the electron transfer is 2. So now I check for, I balance the electron transfer between my oxidation and my reduction. 2 and 2, it's balanced. So now I balance the rest by inspection. And hopefully you realize this is where you have to go back and look at the iodine. So I have 2 times I have 2I and 2I. I have 4 here, so 4 iodine. And that's what I meant by temporary coefficient. So this 2 was temporary. So on occasion, you have to change that coefficient. So don't be afraid to if you need to. So there I've balanced the iodine, 4 times I2, 4 times I. Let's check the hydrogens, 4 times H. Well, let's check lead first, 2 lead, they're balanced. Hydrogen, so 4 times H, 2 times H. You have to make that 2, that's 4 hydrogens. And I have nothing left to balance without changing everything, so oxygen should be balanced. O2, 2 times O, balanced. So I am going to rewrite this one because I have space. 4HI plus PbO2 yields PbI2 plus I2 plus H2O. And then, as I said, final check to make sure it's balanced. Well, we kind of already did that. It is balanced. So that's it. So balancing redox reactions using oxidation numbers, balancing by assigning oxidation numbers, and balancing electron transfer. Again, this takes a bit of practice to get used to the protocol, so by all means, go ahead and practice. And that concludes this video.